Let's continue with our study of unique factorization domains. I defined in the last video what a unique factorization domain is, right? It's a ring which it's an integral domain where factorization exists and is unique. And we also looked at examples where the ring does not have factorization. So there is no factorization. If you could start factorizing an element, it keeps going and you never stop. But in most nice rings that we normally deal with, factorization does exist. For example, we proved that factorization exists in a ring if the principal ideals satisfy ascending chain condition. In particular, if you have a Noetherian ring, factorization exists. Then the question is, a Noetherian ring, certainly factorization exists. The question then becomes, is it unique? And we saw that it's not in general unique. For example, we looked at the ring Z adjoint square root minus 5. It's a Noetherian ring, so factorization exists, but we know that it's not unique. And we want to continue that study today. We want to give a few more conditions for verifying that a ring is a UFD. So let me start today with this proposition. So it has two parts. The first part says let R be an integral domain in which factoring terminates. So as I told you just now, you keep in mind any Noetherian ring, it has this property. It need not be Noetherian, even non-Noetherian rings have this property, but Noetherian rings do have this property, and we know lots of Noetherian rings. Then we say that R is a UFD, then we can say that R is a UFD if and only if every irreducible element is prime. If you recall from a couple of videos back, I defined the notion of prime and irreducible elements in an arbitrary integral domain, and we also proved that in any integral domain, prime elements are automatically irreducible, and we know in general irreducible elements are not prime. In PIDs they are prime because there is a notion of GCD in PID, so we use that to conclude that irreducible elements are prime. Now we are learning that that is the characterization for UFDs, assuming that factorization terminates. And using this part 1, we will prove the second part of the proposition, which says that R is a PID implies R is a UFD. So this is nice. That means any PID that you know has also the UFD property. So our examples of UFDs now increases, right? Because every PID that we know is also a UFD. So let's prove the first part. Second part is very easy if you think about it, because PID in a PID factoring terminates, and in a PID every irreducible element is prime, so PID is automatically UFD. So now let's prove the first part. So what is it that we have to show? We have to show that factorization is unique. Note that in a unique factorization domain, there are three words: unique, factorization, domain. By hypothesis, our ring is a domain, integral domain. It has factorization. So the only remaining thing is that the factorization is unique. So let's prove that. So what does that mean? So let A be any element of R, and suppose it has two potential factorizations. So let's call them P1 through PM, P1 dot P2, P1 times P2 times P3, and so on up to PM. And at the same time, let's say it has another factorization Q1 dot Q2 dot Q3 dot Qn. Okay, so what is the hypothesis here? Pi's and Qj are irreducible elements. Okay, so actually what I am now doing is, the first part is an if and only if statement, right? First part says that a ring is a UFD if and only if every irreducible element is prime, assuming that the ring is an integral domain and factorization terminates in that ring. So I am proving one direction of this. So I am assuming that every irreducible element is prime, and I will prove that it's UFD, and to prove UFD we just need to show that factorization is unique. So So I've taken an arbitrary element, written two possible factorizations. What we want to prove is, we want to prove that n equal to m and pi equals qi after permuting them, right? So of course, if you write pi's in a different order, we do not think of that as a different factorization. So 2 times 3 is same as 3 times 2 in the integers, but that's not a that they do not give two different factorizations of 6. So after permuting, so I should really write this after permuting if necessary, pi is qi. So let's prove this. So without loss of generality, we can assume that m is less than or equal to n, right? M is the number of pi's, n is the number of qj's. Assume that m is less than or equal to n, and we will induct on n. Okay, so n is a positive integer, the number of qj's. So we'll induct on n. So the base case is n equal to 1. If n equal to 1, then m is less than or equal to n. That means m is also equal to 1. That means what? So we have a is equal to p1 equals q1, and that's it, right? So that means factorization is same. So this is trivial. So if n equal to 1, the factorization is same. There is nothing to prove there. Base case is trivial. So now suppose n is strictly more than 1. So we have the factorization that I have written, p1 times p2 times pm, q1 times q2 times qn. Now note that p1 is irreducible. This implies p1 is prime by hypothesis, because I am assuming that every irreducible element in our ring is a prime element. P1 is irreducible because we have taken an irreducible factorization, and by hypothesis of the proposition it is prime. Now what we know is that P1 divides A, right? A is equal to P1 times P2 times Pm. So P1 divides A implies P1 divides Q1 times Q2 times Q3 all the way up to Qn. It divides this product. But a prime element, if it divides a product, it divides one of them. So say P1 divides Q1. So we can assume without loss of generality that P1 divides. Note that P1 divides one of them, maybe it divides Q2, but I can call that Q1. There is no reason for us to not change these things. So I am going to assume that P1 divides Q1. But remember, P1 is an irreducible element. Q1 is an irreducible element. How can an irreducible element divide another irreducible element? This happens only if P1 and Q1 are associates. Remember, that means two elements are associates if one is a unit times the other. So P1 divides Q1, both are irreducible. That means P1 and Q1 are associates. So that means we can write P1. So I'm going to write this as P1 is equal to U times Q1 for some unit U in R. Right? This is the only possibility if you have two irreducible elements. For example, in the ring of integers, 2 is an irreducible element, minus 2 is an irreducible element. And 2 divides minus 2 because 2 is minus 2 times minus 1. Whereas 2 and 3 are not associates and they don't divide each other. So P1 is U1, U times Q1. Now I am going to replace Q2 by U inverse Q2 and Q1 by U Q1. So then what do I have? A is equal to, I am not changing anything, Q1, Q2 up to Qn. I am writing this as U Q1, U inverse Q2, Q3 up to Qn. So nothing is changed. I am just calling this new Q1 and this is new Q2. Okay. So that means, and we now know that this also has this other factorization, P1 through Pm. So now P1, the first term in this factorization is same as the first term in this factorization. So we can cancel this. So cancel P1 equals UQ1. So what do we have then? Then A is equal to P2, P3 up to Pm equal to Q2. Q2 is actually this U inverse Q2, but Q3 up to Qn, right? So we have now again two possibly different factorizations of A, but with one less Qi. So now the number of Qj's dropped by 1. So by induction, remember that we are inducting on n equal to 1 we have settled, and we have taken an n, that means up to n minus 1 we have solved the proposition, proved the proposition. So that means by induction m minus 1 equal to n minus 1 and P2 equal to Q2, P3 equal to Q3 and so on. Okay, so we have proved this by induction. So that means hence m equal to n and so on. P1 equal to Q1 because I have replaced Qi by UQ1. So P2 equal to Q2, Pn equal to Q1, which is what we wanted to prove, right? We have taken two possible irreducible factorizations and proved that really what we have proved is that the number of irreducible factors is same and the irreducible factors are associates of each other. Okay, so I really should say when I write Pi is equal to Qi, I am not really claiming that they are same, but I am claiming that they are associates. So we have shown this. Okay, so I should correct this. Pi and Qi are associates. So we have proved that. So remember, replacing considering associates does not give us a new factorization. So we have the same number of irreducible factors in A and in the two factorizations here, m and n are same, and the corresponding irreducible factors are actually associates. So we have proved one direction, right? We have shown that if you have an integral domain where factorization exists and if irreducible elements are prime, factorization is unique. So R is a UFD. Okay, so now that proves one direction of the first part of the proposition. Now let's prove the other direction. So now we assume that R is a UFD. So now we assume that R is a UFD. What do I have to show? We want to show an irreducible element is prime, right? So that's the proposition. We want to show that if you have a UFD, then every irreducible element is prime. So now I am assuming that it's UFD. I will show that every irreducible element is prime. So let A be an irreducible element of R. Suppose A is not prime. Suppose A is not prime. What does that mean? That means there are two elements B and C in the ring R such that A divides the product, but A does not divide B and A does not divide C. So suppose B and C are in R and A divides BC, A does not divide B, A does not divide C. That means A is not a prime element. We want to get a contradiction. So if A divides BC, this implies there exists D in R such that AD is equal to BC. This is the meaning of, remember, this is the meaning of an element dividing another element. AD is equal to BC. Now since R is a UFD, we can factor B, C, D and obtain different factorizations of AD equal to BC. So what I am really saying is A is already irreducible, right? So we have AD on the one side and BC on the other side. So AD can be factored as A times, A is already irreducible, so let's say D is P1 times Pm. B can be factored as some Q1 times Qn, and C can be factored as some R1 times Rs, right? Every element in a UFD factors uniquely into irreducibles. So A is irreducible, so I am not disturbing A. D can be written as P1 through Pm. B and C are factored like this. That means we have A, P1, Pm is one factorization of AD, Q1 times Qn, R1 times Rs is another factorization of BC. And now claim these are actually distinct. These are distinct. Why? Because A appears on the left hand side, A does not appear on the right hand side. A certainly appears on the left hand side, you can see that A is there. Why does A not appear on the right hand side? A does not appear on the right hand side because, remember, by hypothesis, A does not divide B and A does not divide C. So none of the QIs, A is not here. Remember, if an irreducible element divides another element in a UFD, the irreducible factorization of that second element must contain that irreducible element. And these are irreducible factorizations of B and C respectively. A does not divide them, so A must not be there, right? If 3 does not divide 22, that means in the factorization of 22, so I am just saying something very simple, 3 does not divide 22 in Z, right? That means if you factor 22 as product of irreducible elements, you get 2 is equal to 2 times 11, 3 is not there. Because if 3 is there, then 3 divides 22 by definition. So if A is one of these QIs or A is one of these RIs, then A divides B or A divides C, which we know cannot happen. So that means, and we have said A does not divide B, A does not divide C. So that means A is not on the right hand side, A is on the left hand side. But this violates what? Uniqueness of factorization in R. Right? R is a UFD we are assuming. So in a UFD factorization is unique. But here is one element whose and we found two different factorizations which violates the uniqueness of factorization of R. So this completes the proof of one. Again, let me remind you, this is a very important proposition for us. We have said that if you have an integral domain in which factorization terminates, then completely characterize UFD, we just need to check whether every irreducible element is prime. So R is a UFD if and only if every irreducible element is prime. We proved this first by assuming that every irreducible element is prime. We took two potentially different factorizations and showed that they are in fact same. Then we assumed that R is a UFD, and then we showed that every irreducible element is prime by assuming, by considering a irreducible element which is not prime and obtaining a contradiction. So that is the proof of 1. Let's now prove 2. This is very easy now. If R is a PID, we know that factorization terminates. We can simply say that R is Noetherian. PID is by definition of PID, every ideal is principal. So every ideal is certainly finitely generated. So R is Noetherian. So factoring terminates in R. So we can apply 1. Remember, the hypothesis for 1 is R is integral domain and factoring terminates in R. A PID is automatically an integral domain, and now we have shown that factoring terminates in R. Now to use 1, and conclude that R is a UFD, we show that every irreducible element in a PID, not show, we recall, we have already proved this. If R is a PID, every irreducible element in R is prime. Hence, by the first part of the proposition, R is a UFD. Nice. So the second part is also now complete. So we have shown that any PID is a UFD. So immediately that tells us that the following are UFDs. So let K be any field, then Kx, the polynomial ring in one variable over K, is a PID, is a UFD. We already know that it's a PID because we can divide elements in Kx using Euclidean division, using the degree as our size function. So it's a UFD. Similarly, Z of course is a UFD, that we know, but we know also that Zi are UFDs. Z is something that we are familiar with. Of course, Z, every element is principal, so UFD, PID, hence UFD. But in school, for example, you know that integers can be factored uniquely into a product of prime numbers. So that is already known to us that Z is a UFD. The new thing is Zi is a UFD. So I do not recall if I commented on this. So I'll just comment this without proving it. Recall Zi is a PID. This can be shown using Euclidean division for the with the size function given by so size of sum a plus ib. Remember, an element of Zi is an element of the form a plus ib, where a and b are integers. So if you take the size function to be this, so this is a fact for us. Okay, so maybe I'll write that as a fact. I'm not planning to do this in this course, but it's not difficult to show this. You can read this in Artin's book, for example. Just like we have shown that Z is a PID, where the size function is just the absolute value, you can divide any integer by another integer. Similarly, polynomial ring in one variable or a field, the size function is just the degree of a polynomial. That means size of any polynomial is equal to its degree. Then we can divide and ensure that the remainder has a smaller size, meaning remainder has smaller degree. In this case, the size function is this. So, and we can perform the Euclidean division and show that every ideal is actually generated by a single element. So what do? We take an ideal and take inside that ideal an element with the least size, and then show that that generates the entire ideal. So this is a fact that you can use in the exams and assignments. So Zi is a PID, so it's a UFD by the proposition that we just proved. So now that's good. So we have gotten hold of some more examples of UFDs. But in the proposition, the second part, we only said that PID implies UFD. The question is the converse true? Does a PID, is a UFD also a PID? And the answer is no. So the next goal for us is to show that, this is what I'll do in the rest of this video and then in the next video, to show that the polynomial ring in one variable is a UFD. And this immediately tells us that a UFD need not be a PID. So note that Zx is not a PID, right? Why is it not a PID? The ideal, for example, generated by 2 and x is not principal. We saw this in the video when we discussed PIDs. We saw this. The ideal generated by 2x is not a principal ideal. So Zx is not a PID. Whereas we will prove that Zx is a UFD. So in general, in other words, a UFD need not be a PID. A UFD is not necessarily a PID. Okay, so the goal, and it requires a proof, and it will take us a little bit of time, but we will prove that ZX is a UFD. So as an attempt, what do we do? So how to show that ZX is a UFD. So we are going to use all the results that we have so far showed. So we know ZX is Noetherian, right? The Hilbert basis theorem says that if R is Noetherian, the polynomial ring over R in one variable is Noetherian. So Z is Noetherian for sure, ZX is Noetherian. So factoring terminates in ZX, that's not a problem. That's good. So the F part is clear. Unique factorization domain. ZX is a domain. So let me just write that for clarity. So ZX is an integral domain. ZX is Noetherian, so factoring terminates. By the proposition above, by the above proposition, to show that ZX is a UFD, we need to show that every irreducible element in ZX is prime. Every irreducible element is a prime element. Okay, so that's all, right? In the first part of the previous proposition, we saw that an irreducible element, if you have an integral domain where factoring terminates, and if every irreducible element is prime, that integral domain is automatically a UFD. So we are going to do this part. So this is what we will do. So there are two kinds of irreducible elements in ZX. One is prime numbers, 2, 5, 3, 7, 11 and so on. So we want to show that those are prime, which is the easy part. Every irreducible integer is actually a prime integer. The other thing is, we want to show, so I am going to give you a preview of what we want to do. So let's say this is an irreducible element. What is an irreducible element? Irreducible polynomial. So as I said, there are two kinds of irreducible elements. One is actual integers which are irreducible, in other words prime. Other is irreducible polynomials which are positive degree. So I am going to take we'll settle both cases, but first we'll take an irreducible polynomial of positive degree, right? Remember, if you recall the definition of an irreducible polynomial, it says that it cannot factor into polynomials of smaller degree, which is exactly the definition of irreducible element in an arbitrary integral domain. It has no factorization into further other elements, okay, other than units and associates. So let f be an irreducible polynomial. So note that ZX naturally sits inside QX, right? So ZX naturally sits inside QX. So f is given here. So f can be thought of as, so f is an integer polynomial, but it can be thought of as a rational polynomial. This is the first observation. So it can be thought of as a rational polynomial. So now suppose it's irreducible as a rational polynomial. Suppose fx is irreducible. See, we are assuming that it is irreducible in ZX. We have to prove that it's also irreducible in QX. That we will show later. Suppose it's irreducible. Now, since QX is UFD, remember QX is polynomial ring over a field in one variable. So it's a PID, hence it's UFD. So fx is prime. Fx is a prime element. That means, suppose now let f and g and h be two integer polynomials, and suppose f divides GH. Remember, what am I trying to do? I am trying to show that every irreducible element in ZX is prime. F, I have taken a irreducible polynomial of positive degree. Suppose it divides a product of two polynomials GH in ZX. This distinction is important for us. So f divides GH in ZX. That means there is another polynomial such that f times that polynomial is equal to, there is another integer polynomial such that f times that is equal to GH. But certainly then f divides GH in QX also, because, right, that means f times some f1 is GH where f1 is in ZX. If f1 is in ZX, f1 is also in QX, so this equation also holds in QX, so f divides GH in QX. But this means because f is a prime element of QX, f divides G in QX or f divides H in QX. Now that means that f can be written as, G can be written as f times something in QX, that something is in QX, or H can be written as f times something, that something in QX. But the big question now is, does this imply f divides, does this imply f divides G in ZX or f divides H in ZX? Remember, f, g, h are all integer polynomials, but f divides g or f divides h in QX. The question is, does that division also happen in ZX? So the two things to check is, if you take an irreducible polynomial in ZX, is it irreducible in QX? And if a polynomial divides another, an integer polynomial divides another integer polynomial in QX, does it divide in ZX? So we are going to address both these questions and conclude that ZX is a UFD. So before I stop, I will stop this video and start again next time. But the remark I will make, and I will repeat this also next time, is that the same process, our analysis that we will perform now, also works for if we replace Z by any UFD R. Okay, so Z and ZX and QX is what we are considering, but we can also consider Rx and the quotient field of R bracket X. So, and it will show, so this is the ultimate theorem that we will show. It will show that if R is a PID, sorry, if R is a UFD, then Rx is a UFD. Okay, this is similar to the Hilbert basis theorem. If R is Noetherian, Rx is Noetherian. If R is a UFD, Rx is a UFD. Remember that the same statement is not true for PIDs. We know that Z is a PID, but ZX is not a PID. So it's only true for UFDs. So in particular, after this, we know that all polynomial rings over UFDs are polynomial rings in any number of variables are UFDs, because we can keep attaching variables one by one. So we will stick to Z, but the proof goes through for any UFD. So that's a good exercise for you. As we are doing all the steps, make sure that you prove all the statements for any arbitrary UFD. So let me stop the video here. In the next video, I will continue and prove that ZX is a UFD.